Hello everyone and welcome to lecture. Today's lecture will be about a different way of solving optimization problems with constraints or constrained optimization problems. So one of the issues that we saw when we were going over our general optimization problems was that when we look on the boundary, this becomes a problem of going through and really kind of piecing together what the maximum and min is on the boundary, or when we have a constraint. So one of the big tools that we have at our disposal is another means of doing this exact thing, of dealing with a constrained optimization problem. And this is called the method of Lagrange multipliers. Or the Lagrange multiplier method. And really, this is a very, very convenient method of essentially taking a constrained optimization problem and turning it into an unconstrained optimization problem. So the idea here is that our main problem with the Lagrange multiplier method is that we will try to maximize some multivariable function subject to one or possibly even more constraints, depending on how many number of variables we have. The big application for us is that this method allows us to solve for max and min only on the boundary of a given function or of a given domain. Which was step B in our optimization procedure that we described in the last lecture. So what we'll focus on in this lecture is just maximizing a function of two variables or I guess we should probably say optimize instead of maximize, because really this procedure will give us both the maximum and the minimum. So we'll say maximize / minimize a function of two variables subject to a constraint. Specifically, we'll say the constraint is going to take the form of a level curve. It'll say that we have some multivariable function g of xy is equal to c is our constraint. So essentially what this is saying for a 2D function, as this is in 2D, a picture that we can kind of draw here, is that we'll have our 2D function and this 2D function maybe has level curves that can be relatively complicated. Maybe it looks like this. This corresponds to a specific level of the function where maybe there's a max or a min right here. And same thing right here. So these are just level curves of our multivariable function f of xy in red. Then we have some curve, some constraint curve c. And this black curve is the curve g of xy is equal to c. So the question then is, what is the maximum of the function f subject to this constraint? That's what we're trying to ask here and trying to answer using this method. In other words, if you only move on this curve, the black curve here, g of xy equals c, what's the largest value of the function on this curve and only on the curve? If you just stay on the curve and you only consider points on the curve. This is exactly what this method will answer for us. So that when we have a problem like this, this is called a constrained optimization problem. Because we're trying to optimize the function f subject to the constraint, or taking into account the constraint. Now, we already know how to solve an unconstrained optimization problem, so an optimization problem without a constraint at all. And the key trick in this method, the Lagrange Multiplier method, is to turn our constrained optimization problem into an unconstrained optimization problem by introducing a new variable. This new variable we call a Lagrange multiplier. So what we're going to do, and what we do here, is we transform the constrained optimization problem into an unconstrained optimization problem. Which we know how to solve. You just find the critical points and verify that those critical points are in fact global maximums of the function, this new unconstrained optimization function. And we do that by introducing what's called a Lagrange multiplier, which is a new variable. And a new function that we call the Lagrange function. These are the two big new introductions that we have to make to do this. And for this problem that we're considering now, a function of two variables with one constraint, the Lagrange function is going to be a function of three variables, or the two original variables, and of a new thing that we'll call the Lagrange multiplier. We'll call it lambda. So lambda here is the new Lagrange multiplier. And this is constructed relatively simply. We just say it's going to be the original function, lowercase f of xy, minus the Lagrange multiplier times the constraint function minus c. Because you'll recall that the constraint function, if we have a g of xy equals c, this is the same as the equation g of xy minus c is equal to 0. So you'll see why this is important in one moment. So for this new function, we want to think about how to optimize the new function. So how to optimize the function capital F. And you'll remember from our previous procedure that the first step is to solve for all critical points of capital F. And this is going to be critical points of either type 1 or type 2. We're going to only focus on critical points, or on functions f which have critical points of type 1, because it makes the analysis a little bit simpler. But you'll recall that in order to do this, to solve for the critical points of capital F, the gradient of capital F has to be equal to the 0 vector. These are all critical points of type 1 that we classified earlier. So any point with a gradient of capital F is equal to the 0 vector is a critical point of type 1. Well, this is the same thing as having the x partial derivative of f be equal to 0, the y partial derivative of capital F be equal to 0. Then because f is a function of 3 variables, it also means that the partial derivative of f with respect to lambda also has to equal 0, because capital F is a function of those 3 variables. And this gives us a system of 3 equations that each have to hold at any critical point of this new Lagrange function, capital F. And it turns out that these 3 equations have actually a lot of geometric significance. What this is saying for us is it's saying that if we take the x partial derivative of this function right here, this is the same thing as, well, the x partial derivative of a lowercase f minus lambda times the x partial derivative of g It's important to denote here that this capital F is, this gradient means the f partial derivative of x with respect to x, the f partial derivative with respect to y, and the f partial derivative with respect to lambda, because this is a function of 3 variables. So we have that this has to be equal to 0. And similarly, when you take the y partial derivative, you have that the y partial derivative of this expression has to be the y partial derivative of lowercase f minus lambda times the x, or the y partial derivative of g has to also be equal to 0. And then lastly, when we take the lambda partial derivative of this expression right here, you get that negative g of xy minus c has to be equal to 0. So what this is showing you is that any local minimum of the function capital F, of the Lagrange function, has to satisfy equation 1, equation 2, and equation 3. And what that's meaning for us, we will take a look at equation 3 first. Right? Equation 3 being satisfied means that at any local minimum of the Lagrange function, if g of xy minus c has to be equal to 0, then g of xy has to be equal to c, which means that the constraint is satisfied. This is the first big point here, that the constraint has to be satisfied at any local minimum of the function capital F. And what that means is that if we have some local minimum, say we have some local minimum, we'll say x star, so some solution to these three equations, local minimum or local maximum. So x star, we'll call it y star, and lambda star. Then also, if you look at the Lagrange function, the value of the Lagrange function at this critical point of capital F is going to be equal to the value of f, lowercase f, just at x star, y star. Because if equation 3 is satisfied, that means that g of xy minus c is 0. So at that point, this term is going to be 0. So the constraint is going to be satisfied, which means that x star, y star, lambda star could be a saddle point of the Lagrange function. But if it's a local max or a local min of the saddle function, then it's like if f is maximized or minimized, then so is the function f, lowercase f. The constraint is also satisfied. So this is really a big thing. This is the power of the Lagrange multiplier method, is that the maximum and minimum of capital F directly correspond to maximum and minimum of lowercase f, while also satisfying our constraint. So this is a very cool and very neat trick mathematically. We can also interpret equations 1 and equations 2 together as follows. This is saying that the derivative of f, partial derivative of f with respect to x, and the partial derivative of f with respect to y have to be equal to lambda times the x partial derivative of g and the y partial derivative of g in vector form. Well, this is an equation that's directly telling us that the two-dimensional gradient of the function f, the gradient vector of the function f in 2D, has to be equal to a constant lambda, that Lagrange multiplier constant, multiplied by the gradient of g, our constraint function. The equations 1 and 2 are telling us actually geometrically how to go through and solve for these optimum points. That at any point where the gradient is a constant multiple, so pointing in the same direction, the gradient of lowercase f is a constant multiple of the gradient of g, you have a maximum or a minimum on that boundary point or on that constraint point. And very often we can use this graphically to automatically determine very quickly where the potential local mins and maxes are. So for instance, if we look at this picture right here, you see that there's only a couple spots where the gradient vector of g and the gradient vector of f are pointing in the same direction. Right here, this is an example of a point where the gradient of g is pointing in the same direction as the gradient of f. So this is a potential local max or min of our function right here, because the gradient at that point, and the gradient of the constraint at that point is pointing in the same direction as the gradient of g. If you look around the boundary, there's another point right here, it looks like, where those two gradients are going to point in the same direction. Right here looks like one, and right here as well. So those are all potential max and mins on the boundary, because the gradient of the constraint function is pointing in the same direction as the gradient of the function we're trying to maximize. So let's see this and how to do this for a couple of different examples, and we'll see that this is a very, very powerful method for optimization. So what we'll do here is pull in the example that we started with and we used in the optimization lecture to show that this is a new method that's giving us the exact same answers that we got before. This is the example of maximizing and minimizing the function f of xy is equal to x times y on the boundary of an ellipse, or on the ellipse x over 3 squared plus y over 2 squared is equal to 1. So we have a function that we're trying to maximize, and we have our constraint, which is that this function g of xy is equal to 1. That's the curve given by the ellipse. And like I mentioned before, if you draw the level curves of a function correctly, you can directly, many times, just kind of tell what the solution is going to give you before you even go through and do the actual math on it. So let's do that and just show that we can kind of see where the maximum and minimum of the function are going to be without even using and going through and doing this procedure. So first we'll draw the ellipse curve. Is going to look like this, roughly speaking. This is the equation g of xy is equal to 1. And then we'll also draw the level curves of this function, which are going to correspond to the following. At 1, this function is 1, 1, this function is 1, 1. At 2, 1, this function is 1 half. And at 1 half, 2, this function is 1. We have the same story down here for -1, -1. So this corresponds to the level curve c equals 1. C equals 1. At c equals 0, you have a level curve that looks like this on both the axes. And for c equals -1, you have a hyperbola that looks like this, and then same thing on the opposite side as well. And you can draw more level curves for higher and higher values of c. And you're just going to get hyperbolas for larger values of c that are sort of stretched out a little bit more. So you should hopefully be able to see that the gradient of this ellipse, of this level curve for g, is going to be pointing at these varied points perpendicular when you're at a 45-degree angle in either for any one of the quadrants, and as well the gradient of the function f at that point will also be perpendicular. So in orange here I've drawn out what the gradient of f looks like, and then the gradient of g will always be pointing out. And it's at those 4 points where the gradient vectors of each of these two curves point in the same direction. So without even doing the mathematics out on this, and going through and actually solving the system of equations that we get, equation 1, equation 2, equation 3, we have that we can identify with just the level curves in the constraint curve where the potential max and mins of our function are on this boundary, on this constraint curve. And if you remember from the previous lecture, those are the 4 points that we solve for. So those are the correct locations of the max and mins. And so what we want to do is go through and actually do the procedure and show that it actually works very well. And we can go through and solve the system of equations that we get with the Lagrange function. So the first thing that we need to do with this procedure is set our Lagrange function. And this is going to be the function that we're optimizing, which is x times y minus lambda times our g function, which is x over 3 squared plus y over 2 squared minus c, or minus 1. So this right here is the correct Lagrange function for this problem. Once the Lagrange function is set, then we can go through and follow our optimization procedure for this Lagrange function. So what that involves is solving for the critical points of the Lagrange function. which will give us equation 1, which is that the x partial derivative of capital F should be equal to 0. The x partial derivative of capital F is going to be y minus, and then when you go through and compute the derivative with respect to x of this expression right here, you're going to get 2 lambda x over 9. And there's no more x variables up here, so this is it right here. This is our equation 1. This is the partial derivative of capital F, the Lagrange function. Now it turns out that this is going to be a little bit more convenient to write in the form y is equal to 2 lambda x over 9 because ultimately we're going to plug this into the constraint function, so we should also square this as well. Get y squared is equal to 4 over 81 times lambda squared x squared. So these are equivalent notations for, or equivalent representations of this expression right here. Equation 2 is saying that the y partial derivative of the Lagrange function at any critical point has to be equal to 0. And the y partial derivative of our Lagrange function is going to be x minus lambda times y over 2. When you go through and take the partial derivative of this right here, this is exactly what you'll get. And again, rewriting this in the form x equals lambda y over 2, or x squared is equal to 1/4 times lambda squared y squared, will be convenient for us when we plug into equation 3. And so the last equation that we have when we optimize or look for the critical points of capital F, our Lagrange function, is going to be equation 3. Or our constraint equation is saying that the lambda derivative of f has to be equal to 0. This is going to be negative times x over 3 squared plus y over 2 squared minus 1 has to be equal to 0, which is just the equation of our constraint, or x over 3 squared plus y over 2 squared is going to be equal to 1. So the main idea here now is that we have 3 equations, we have 3 unknowns, and if I can solve this system of equations for our unknowns, x, y, and lambda, we hopefully have solved for any and all possible solutions to our optimization problem. And it turns out that this is going to give us exactly the 4 solutions that we found the other day using the parameterization method for optimization on a boundary. So we'll start by considering and trying to eliminate variables by plugging equation 1 into equation 3. So if we take equation 3 and we plug equation 1 into equation 3, equation 3, remember, I'll just write that right here so we can see directly what we're plugging into. Equation 3 is the equation x squared over 9 plus y squared over 4 is equal to 1. And if we plug in for y here, we get x squared over 9 plus y squared, which is 4 over 81 times lambda squared x squared over 4 is equal to 1. When we divide by 4 here, the 4's cancel out. And I can also factor out an x squared to get the equation that x squared, you can factor out a 9 as well, x squared over 9 times 1 plus lambda squared over 9 is equal to 1, or x squared over 9 is equal to 1 over 1 plus lambda squared over 9. So this is, plugging equation 1 into equation 3 eliminates y and just gives us a dependence of x on lambda. It tells us how x depends on lambda. We want to do the same thing for equation 2 and equation 3. That is, plug equation 2 into this expression for equation 3. And the idea is that this is actually going to eliminate x for us in this equation. So when I do that, I plug in for x squared. X squared is lambda squared times y squared over 4 from before. If you remember from before, we ended up finding that x squared was 1/4 lambda squared times y squared from equation 2. So we plug it into equation 3 to get x squared over 9 plus y squared over 4 is equal to 1, which is the same if I factor out this y squared over 4 as the equation y squared over 4 times 1 plus lambda squared over 9 is equal to 1, or lastly that y squared over 4 is equal to 1 over 1 plus lambda squared over 9. So we've solved for the relationship between x squared and lambda, or between x and lambda. We solved for the relationship between y and lambda. The last thing to do is to eliminate both variables x and y. So plug this expression and this expression into our equation 3 and isolate lambda, thereby solving for lambda. We get one equation that we can solve for lambda. So we're going to take both of those two results and plug into equation 3. Remember, equation 3 is x squared over 9 plus y squared over 4 is equal to 1. And we've solved for x squared over 9 and y squared over 4. They're the same thing. X squared over 9 is 1 over 1 plus lambda squared over 9. And y squared over 4 is also 1 over 1 plus lambda squared over 9. Which gives us the equation 2 over 1 plus lambda squared over 9 is equal to 1, or 2 is equal to 1 plus lambda squared over 9, or 1 is equal to lambda squared over 9, which means that lambda squared is equal to 9. So lambda is equal to plus or minus the square root of 9, which means that lambda is equal to plus or minus 3. So the two Lagrange multipliers that work for this problem are plus and minus 3. Not only that, we can actually go through and now that we have our two possible values of lambda, and actually solve and use this in our equations, our previous two equations. So from our previous two equations, we take this result and we plug back in from our first equation. We can call these two equations, if you want, equation 1 star and equation 2 star, just for labeling purposes. So this last step was taking equation 1 star and equation 2 star and plugging them into equation 3 to solve for lambda, to kind of eliminate both variables x and y. If we now take another look at equation 1 star gives us x squared over 9 is equal to 1 over 1 plus lambda squared over 9. And if lambda is plus or minus 3, then that squared is going to be equal to 9. So x squared is going to be 1 over 1 plus 9 over 9, which is 1, or 1/2. Which means that x squared is going to be 9 over 2, if I multiply both sides of this expression by 9, or x is going to be plus or minus the square root of 9 over the square root of 2, which is plus or minus 3 over the square root of 2. Likewise, we can do this for equation 2 star. And remember, equation 2 star is giving us that y squared over 4 is equal to 1 over 1 plus lambda squared over 9, which is 1 over 1 plus 1 when you plug in plus or minus 3, or 1/2. So that gives you that when you plug back in, or when you first will solve for y squared is equal to 4 times 1/2, or 4 over 2, which means that y is equal to plus or minus 2 over the square root of 2 when you take the square root of both sides. And what this gives us then is exactly the same solutions that we found with the previous method. They're the directly, the same solutions that we found using the parameterization method for the boundary, but it's with an entirely new method of calculating this optimization, the solution to this constrained optimization problem. This is really incredible. There are two methods of doing this, and this method of solving a constrained optimization problem is very, very powerful. It can be applied in a wide variety of scenarios, and using many different kind of tools in some sense. So I guess what I'm trying to say is that this is what I've shown is only for a function of two variables and a constraint with two variables, but this idea extends to a wide variety of problems. Optimizing a function of, say, 5 variables with 2 constraints, all of these methods can be directly extended, which is very, very incredible. And what's amazing is that using this method, if you use the Lagrange multiplier method, you can get a nice graphical depiction of exactly where the max and mins of the functions are, of a given function are, with a constraint on a constrained optimization problem. And you can see very clearly in this picture that we're able to draw a picture of the level curves and the constraint function and immediately tell where the max and min values are going to be on this constraint curve without even going through and doing this procedure, which is sometimes a little bit long, but you can see very clearly that it produces the correct answer. Both for the points, the x and y values that are the max and the min on the constraint curve, and also for the Lagrange multiplier, which is in some sense a constant of proportionality between the gradient vector at a point and the gradient of the constraint at a point. So here we see a verification plot that very clearly shows that the solution we obtained via Lagrange multipliers is the correct solution, and it's really, in some sense, the same solution that we found when we went through and did the parameterization method, so for the previous lecture. However, what I've added to this plot is the gradient vector and the gradient of the constraint function, and that's these green arrows down here and the orange arrows. You see the gradient vector at each one of these points for the function is pointing in the correct direction. Here it's pointing in this direction, whereas here it's pointing in this direction. And at each one of these solutions that we found, the gradient vector is very clearly pointing in the same direction or parallel to the constraint vector, which is the green vector here. So the gradient of the constraint function. And you very, very clearly see here, and then if we rotate the plot a little bit, here and here as well, for each one of these points that we found in the boundary, these are the only points where the gradient vector of the function is parallel to the gradient vector of the constraint function. And the constant of proportionality is exactly the Lagrange multiplier that we found, which was 3. The scaling is a little bit different here because I really wanted to blow this up and kind of emphasize the relationship, but the idea is that this is exactly what that Lagrange multiplier is representing. It's the constant of proportionality that relates the gradient of the constraint to the gradient of the function itself at all of the potential max and mins on the boundary that we solve for using the Lagrange multiplier method. So this is a very neat diagram.